Hey, hello everyone. Welcome to my next class. Today we are going to talk about conformations of cycloalkanes. So last class we talked about conformations in normal alkanes. This time we are going to talk about cycloalkanes, right? So cycloalkanes, it can be 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring. We are going to look how do they appear, how do they really exist. Do they exist as we think of them, or do they have some stable way of staying at the least energy possible? Before we discuss that, we have to know about two problems which normal alkanes, cycloalkanes face if they don't undergo some stabler form of conformation change. Okay, the two problems, the issues which they face, two kind of strains they face. First one is Bayer's angular strain, or it is sometimes called just as Bayer strain. Second one is called as torsional strain. Okay. So what is Bayer's angular strain? Bayer's angular strain is nothing but a carbon is there. If it is sp3 hybridized, the angle we expect is to be 109 degrees 28 minutes. If the angle is more than that or less than that, it is not comfortable. It wants angle to be 109 degrees. So when the angle of a molecule of a cyclohexane is not at the angle which is expected, then the strain which it faces is called as Bayer's angular strain. And torsional strain is something like two substituents are there when they are in when they eclipse each other, and because of that they produce what is called a steric strain, and that is called as torsional strain. When we look at the examples, we will understand more clearly, but please understand two things are there: Bayer strain and torsional strain. Bayer strain is all about angle, torsional is all about eclipsing substituents, steric hindrance, right? We'll do one by one. Let's start with cyclopropane. Okay, so cyclopropane is 3-membered. Okay, so cyclopropane, as you can see, it has 3 carbons, and the structure, of course, what comes to our mind is trigonal planar. Interesting, that's the only possible structure for cyclopropane. You understand, it's a very strained ring. Not much movement is possible. Flexibility is very low because only 3 carbons are there. It cannot move and take some other conformations. So that's why this is one of the most unstable ring. Okay, so what's the bond angle? So bond angle, angle will be 60 degrees. 60 degrees. This also will be 60 degrees. It's equilateral triangle, so this angle has to be 60 degrees. Now what? This carbon, and this carbon, all 3 of them are sp3 hybridized. So sp3 hybridized means what's the angle we expect? We expect to have 109 degrees 28 minutes. But what's the angle? 60 degrees. Is almost close to 40 degrees, close to 40 degrees angular strain. So huge amount of what is called as Bayer angular strain is there, very unstable. Apart from that, it also faces very strong torsional strain. Now look at these hydrogens. Now what, imagine this carbon, all are in plane, and that's what they are all on the board. So they are all, these bonds are actually on the board, and one hydrogen is coming outwards and one hydrogen is going inside the board, kind of V. Okay, so same V here also, and same way is here also. Now what is happening actually? This hydrogen is eclipsing this hydrogen, also it is eclipsing this hydrogen, and these two hydrogens are also eclipsing. Similarly, all the hydrogens which are under the plane, which is away from the viewer, they are all eclipsing each other, which is below the plane. So these three hydrogen faces torsional strain, and the other three, the behind hydrogen, they also face torsional strain. So this is very, very unstable, and thermodynamically these are one of the most unstable rings. Three-membered rings are thermodynamically very, very unstable. Okay, just one thing before I proceed. Three-membered ring, though they are thermodynamically very unstable, they are kinetically very favored. Why kinetically very favored? What do I mean by kinetically very favored? Kinetically very favored means it occurs very fast. That means intermediate is stable. Imagine I am having something like oxygen is there, and here some chlorine is there. If the attack has to happen so that Cl leaves, this can happen very fast. But at the end, product may not be stable, so it may not form. But if a reaction is going through three-membered ring, reaction will happen very rapidly, because three-membered ring is kinetically very, very favorable. Please remember this. Three-membered ring is kinetically very, very favorable. So if in the mechanism it goes through three-membered intermediate, very favorable. But if it ends up in forming a three-membered ring, it will try to avoid that, because three-membered ring is kinetically, thermodynamically unfavorable. Right. So now this is the fate of it. Three-membered ring, it cannot move. There is no flexibility. Nothing can be done. So it stays like that, very, very unstable. But it tries something to be stable. What does it try? What it does is, now if this orbital is like that, lot of strain is there. So what it tries to do is, after all, you understand how this bond is formed. Bond is formed because this carbon is there, it has a sp3 hybridized orbital. So what it does, it instead of the plane, no, it is little bit outside. Similarly, even this, no, this bond, so the sp3 hybridized orbital is little bit outside. So this has one electron, this has another electron. So the bond is not exactly on the plane, but it is kind of outside. It is called as bent bond. Similarly, this also, if you look, it will be like that, and so it has a bent bond. And there are numerical evidences, experimental evidences to prove this. So the bonds are not very, very planar, but they are little bit outside, and that cannot be called as conformations, because not the atoms are moving, it's not the position of the atoms are moving, but bond a little bit outside than being in plane, so it is called as bent bond. What is the significance of this bent bond? Now this is very interesting and it's very important also, please pay attention. Okay, so what it means is, in the bent bond, there is more of p character than sp3 hybridized carbon. What it means is, basically you see, if you have sp3 hybridization, what is the angle you expect? 109 degrees, 109.5 degrees, let's put like this. If you have sp2, what is the angle you expect? What it should be? It should be 120 degrees, and when it is sp, hybridization angle is 180 degrees. So what you are seeing is, from sp to sp2, the p character has increased, bond length has dramatically reduced. Similarly, from sp2 it has become sp3, bond angle has again reduced. You see what is the bond angle here? It is 60 degrees. So it's a bent bond, it will not be exactly 60 degrees, little more than 60 degrees, but still it cannot reach 109 degrees. To accommodate that, what happens is, there is increase in p character of this orbital. There is an overlap of orbital. After all, its bond is formed because of overlap of orbital. Now the overlap of orbital, the orbitals p character increases. And some books like Advanced Organic Chemistry by Jerry March, they use the word called as sp5. You understand? sp5 and all are theoretical terms. It may not have any meaning, but they are trying to say that there is more of p character. So it has more of p character, so that the bond angle needed is not 109 degrees but little less than 109 degrees, and there is a kind of bent bond. There is a kind of bent bond. Okay? But now you understand, sp5, theoretically what we are saying, it is not possible because it has to be sp3. This carbon is sp3 because carbon has only s and 3p orbitals. So if there is increase in p character, somewhere it should be compensated for the decrease in p character. For the increase in p character, it has to be compensated by decrease in p character. So what happens here is, there is decrease in p character of this orbital. That means there is increase in s character. Increase in s character. Okay, so carbon bond, there is in carbon bond there is increase in p character. So between CH bond there is increase in S character. And how do I know what I am saying is truth? It can be known if this proton is little more acidic than your normal alkanes. We have talked about it. Once again I'll revise it for you. Between ethane and ethine, let us just take this one. Between ethane and ethine, this proton is more acidic. Why? Because this bond has more of S character, because this bond is sp hybridized. This bond is sp hybridized, whereas this bond is sp3 hybridized. So when there is increase in S character, now you know S orbital is closer towards the nucleus than p orbital. Understand that? S orbital, because of its shape, it is closer towards nucleus than p orbital. So it faces lot of attraction from nucleus. So if electrons get pulled, the electrons are more close towards carbon than hydrogen. Appreciate this point. This carbon, see, this hydrogen has only s orbital. So we are not talking about the orbital involved with hydrogen. We are talking about the orbital involved with this carbon. So this carbon, this orbital has more of S character. So if there is more of S character, these electrons are closer towards carbon. So the bond becomes weakened and this proton loss can be easy. And it has been seen that these protons are more acidic than normal alkane proton. This is what they will be asking you. Okay, this is a very important point. This proton of cyclopropane is little more acidic than normal alkanes protons acidity. Okay, I hope I am clear. Let's move to the next molecule. The next molecule is cyclobutane. So when we think about 4-membered ring, we think of this. And if that is the case, what's the bond angle? 90 degrees. So of course it is facing Baer's angular strain, and then it also faces torsional strain. So what happens is this hydrogen is blocking this hydrogen, the behind hydrogen is blocking this hydrogen. Similarly, all the 4 hydrogens are eclipsing each other, and all the 4 hydrogens behind the board, they are eclipsing each other. So they face lot of torsion, so torsional strain, and therefore this is not how cyclobutane exists. How cyclobutane exists is like this. You can call it envelope, but they don't call it envelope for some reason. So here what happens is now torsional strain is dramatically reduced. Torsional strain is dramatically reduced because now hydrogens are not eclipsing each other. Now hydrogens are not eclipsing each other. Bond angle is still not 109 degrees, okay, but it is approaching towards 109. So there is definite reduction in the Baer's angular strain, but most importantly this conformation is preferred because torsional strain is lost. Before there was fantastic huge amount of torsional strain. All the hydrogens were eclipsing each other. Now that strain has gone. Remember once again, 4-membered ring is neither kinetically nor thermodynamically favored. That means if the end product is 4-membered ring, it will try to avoid a reaction, will try to avoid that forming that product and form something else if it is possible. If not possible, of course it has to form. And 4-membered ring is kinetically also not favored. That means given a chance, if it has to go, it can undergo through a transition state of 3-membered ring or a 4-membered ring. It will go via 3-membered ring and not 4-membered ring. Why? Because very, very unstable. So if you look at the activation energy, so for 3-membered ring, it doesn't need so much energy because they are close by, they attack fast, so kinetically favored. Whereas when I come to 4-membered ring, huge amount of energy is required to form this 4-membered ring, and therefore kinetically, when we talk about kinetics, we talk all about the stability of the transition state or the stability of the intermediate. So 4-membered transition state or the intermediate is also very, very unstable compared to even 3-membered ring. So 4-membered ring is neither kinetically nor thermodynamically favored. Very, very important. Please remember this. Last we'll come to cyclopentane. So cyclopentane, we can think of 5-membered ring is like this. Okay, so what we think when we think of cyclopropane, we think of cyclic planar structure. Now what will be the angles? If you use little geometry, you will know that this angle should be 108 degrees. 108 degrees. Now it's very, very close to your expected 109 degrees 28 minutes of that of sp3 hybridized carbon, tetrahedral carbon. So you should feel that this should be the conformation which is stable. It should remain, it should look like this. But no, there is a problem. Of course, the angular strain, the Baer's angular strain is minimum, no problem. It can stay like this. But still it has another strain. What's the strain? Of course, that is the torsional strain. This hydrogen blocks this hydrogen blocks this hydrogen, this blocks this and this hydrogen. So all the hydrogen towards the viewer are eclipsing each other, creating lot of torsional strain. Similarly, all the hydrogens away from the viewer, that is behind the board, they all are blocking each other, and therefore this cyclic planar structure is not favorable. But remember, 5-membered ring is kinetically more favored than even 6-membered ring. Thermodynamically 6-membered ring is most favored. Okay? 5-membered ring because it is smaller, so it's easy to form. It is faster to form, and therefore 5-membered ring is actually kinetically very little, but little more favored than 6-membered ring. 6-membered ring is most favorable, you know, because you see everywhere in the in the biology, everywhere you will find 6 membered ring. You have glucose 6 membered ring. Most of the places you will find 6 membered ring. Okay. So what's the conformation in which this cyclopropane exists? So cyclopropane exists in two conformers. One of them is called as envelope and another one is called as half chair. There will be equilibrium between both of them. But basically what happens, to understand this, it's like this. It's not that this carbon are on plane. You have to understand this is coming outside and then going inside. So it's like, if you imagine this is on the board. So this board, this part is on the board. And this part is coming out and then going in. So that's how half chair it is. So angle is still close to 108 degrees, or rather it's approaching 109. But the good part is the torsional strain has dramatically reduced. Now there is no torsional strain. The hydrogens are no longer blocking each other in eclipse structure. That is one. Another, this is the one. So it's like you can imagine this is coming on the plane, this carbon and this carbon. And then this carbon is going away. It's not in the plane, okay? This is going away from the board and then these two are there. So basically again angle remains 109 degrees. But again the good part is torsional strain is dramatically reduced. So what you have to remember from examination point of view is cyclopropane exists in two conformers, that is envelope and half chair. It is more so not to reduce the Baer's angular strain but to reduce the torsional strain. Okay, and then we have cyclohexane. I don't think today we'll do in this class because because it is a big topic, and I will be discussing exclusively for cyclohexane in the next class. Thank you very much.